So let me get started, and you have the table of contents on the right screen, and we have the introductory material here up to page 125, and the intermediate growth models thereafter, which will be this afternoon. And at the very end, hopefully you're not too exhausted at the very end, because then we switch gears and talk about categorical outcomes. Growth modeling with categorical outcomes, which in itself is a lead-in to tomorrow morning's treatment of very, very skewed data, data with strong floor effects, where we're going to do so-called two-part modeling and zero-inflated modeling, which then requires the knowledge of categorical growth modeling. And here then a good prerequisite, not a prerequisite, but a good introduction to this topic, it would have been topic 2 that we taught in March, which was focused on categorical data analysis. So if that goes over your head today, then you can go back to that topic or that video from day 2 and study up on that. So here, just briefly, because most of you have seen this before, the background for the Mplus program is to try to bring together a lot of good statistical ideas. They are spread over many journals and in many pieces of software, so you can now spend your whole life within one piece of software. And integrating it into one framework with one language that's simple, and while still having a very powerful modeling capability, so which keeps getting expanded thanks to a very good team that we're working with. It's a team that moves forward almost too quickly. Well, I had to quit my job at UCLA to keep up with them, so that's the indication. So Mplus then started in 1998. We got an SBIR from NIH in 95, 94, I guess it was, which was the inspiration of, or the vehicle that made this all possible. And November 2007, version 5 came out, and then here in the blank there is version 5.1, which came out in May. And as very often is the case with Mplus, I could just as well have been called version 6 because there's so many new features in it, but we didn't have time to create a new cover for the user's guide. That was mainly the reason. So, you know, practical reasons. But in May 2008, version 5.1 came out. So you should use 5.1. There's a distinct difference between the versions, certainly. And version 5.11 is in the works for, with some improvements over particularly in the area of the new things that got introduced. Whenever you introduce a new thing, a new feature, you can then improve it speed-wise and otherwise. And that's particularly the news that's being improved is in the factor analysis and structural equation modeling area, where we've made a concerted effort to bring together, to better integrate exploratory factor analysis with structural equation modeling. So you can actually have now in Mplus exploratory factor analysis measurement parts. You don't have to be forced to come up with a confirmatory measurement model specification for SEM, for structural equation modeling. But that's another topic. I should mention also that on our website is a new section called Mplus Web Talks. And that is, so that's web videos that you can watch for free on your computer. And that then talks about new features in Mplus. So it's a little bit of statistical methodology and a lot of applications. So I think there are 4 or 5 talks that are sitting on the website there, also with help of the statistical consulting service at UCLA. So here's the Mplus team. Linda, who is actually my wife, and Thuy Nguyen, one of the programmers, and Tiomer Asparohov, the other programmers, and then the office staff. So there. And the idea is that we want to bring all these techniques together with the help of latent variables. So the strength of the framework is that we combine continuous latent variables and categorical latent variables. And today and tomorrow we're going to talk today we're not going to talk about categorical latent variables at all. A little bit tomorrow. But the categorical latent variable topic is really for Michigan, for Ann Arbor, with these kinds of latent class and mixture models, and be it in the cross-sectional case or in the longitudinal setting, the growth mixture models. So we're going to focus on continuous latent variables, just like we did in March in the SEM and factor analysis area. We can talk about factors and factor analysis as a basis for growth modeling, but we're going to make it clear that that's just the same as what statisticians call random effects. Random effects, continuous latent variables, which we're going to use in our growth curve models. In March 2009, we're going to use those random effects also in multi-level models. And we're going to talk about how a growth model can be seen as one case of a multi-level model, but doesn't have to be seen that way. We're going to certainly talk about missing data. So if you have missing data on a continuous variable, well, then you have a continuous latent variable, an unobserved variable. And we're going to do missing data modeling certainly tomorrow. So the framework is like this with a notation and model diagrams that are pretty consistently formulated. Boxes for observed variables, circles for latent variables. X variables are covariates, variables that we do not impose a model structure on, just like we don't impose a model structure on covariates in the regression analysis. We have dependent variables. We're going to call them Y or U. We call them U when they are categorical, and otherwise we call them Y. We're going to work with continuous latent variables, factors, or random effects, as it will be today. Random effects in growth models. Categorical C is a categorical latent variable, and that is then a topic for Ann Arbor again. So we have all these relationships, possible relationships between these variables, and it's interesting that we can integrate them into one framework now. Usually there's been separate frameworks, A and B, like this, where people have moved around in their own spheres, working with continuous latent variables only, and then there's the group of researchers working with categorical latent variables only, and they never meet. So we thought they should meet and get together within this box, and also be able to do that in a multi-level fashion with within-level variation on covariation and between-level. Or we could just as well have said level 1 and level 2. And again, this is how excited we are about that. So we're going to talk about X's as background variables or covariates, Y as dependent variables, U as another dependent variable, and keep that nomenclature throughout. Although today we're not going to work with F as much. F is a factor measured by multiple indicators. We're going to draw the analogy between factor analysis, particularly confirmatory factor analysis, and growth modeling. But we're going to give other names to the growth factors than F, as it turns out. Now, many people think of Mplus as a structural equation modeling program, but that's quite a limited view. It's really several programs in one. It's at this point now, a uniquely good exploratory factor analysis program. It has more features than any other exploratory factor analysis program, particularly with new rotations and the possibility, for instance, to do exploratory factor analysis in multiple groups. So you can impose the same measurement structure for males and females, but in each group it's an EFA measurement structure, not a CFA measurement structure. You could do longitudinal exploratory factor analysis, time point 1 and following the people to time point 2, and test for invariance of factor loadings across time in an EFA. So we're sort of marrying, bringing together EFA and CFA. And also, I think Mplus at this point is uniquely strong in structural equation modeling. It's a very good item response theory analysis program, very good latent class and latent transition analysis program. It does survival analysis, both continuous time and discrete time survival analysis. And actually, in the classic continuous time survival analysis framework, Cox regression, it can do things that can't be done in other programs, including working with the latent variables, be they continuous or categorical. So we're quite excited about that. That's sort of a sleeper that people are gradually starting to discover. And then growth modeling, of course, which we'll talk about today, all the features that are very specific and go beyond what you can do in programs like SAS-Proc Matrix, HLM, or other programs. Multi-level analysis more generally. It's a very strong program in that area. And the complex survey data analysis, it's been a special effort with support from NIAAA and another SBIR to the Mplus business for an SBIR, a contract for developing complex survey data analysis features, sampling, weight handling, clustering, stratification, in all of these models that we talked about. So going beyond what you can do in programs like Sudan. And then adding to that possibility to do Monte Carlo simulations, that is being able to study the quality of your analysis, your estimates and standard errors, which you may want to do not only if you're a methodologist, but also if you're a substantive researcher, to study the quality of your findings. And all of that is fully integrated then in a general latent variable framework. It's not that you have one program for each, but actually all of this is integrated. And that was the tricky part, to do that in an effective fashion. So, all right. So Mark, is everything going okay back there? This is the video recorder. Camera's up here somewhere, so watch out on this. The first few rows here, don't bite your nails or do something strange or anything. Now, where are we? If you didn't catch, you came in late or didn't, if I went too fast, here's the overview of the 8 topics. So all of those features that I talked about in Mplus are explored in these 8 days. It used to be that we could teach it in 5 days in Alexandria. We actually did 5 days in a row because we were so eager to talk about everything. But it exhausted us and the audience, and we still weren't able to cover everything, so it turned into 8 days split into 4 parts. So we did this 1 and 2 in March, like I said, and here we are, August 21st, I believe it is. And here is the forthcoming topics, ending in March 2009. So let's take a look at some data. So what I'll do is I'll try to talk about these topics on a couple of different levels. The very applied level, where you can understand where we're heading without understanding formulas or details of the statistics. And on the other level, I'll try to give enough statistical details so those of you who are statistically inclined know exactly what I'm talking about. We are going to present some formulas, but they'll be very simple ones. And even for those of you who don't like formulas, who skip over the formulas to read the words that follow the formulas, like me, they can they should look at these formulas because they're simple enough, and you will then more easily be able to read papers and know what they're talking about. So some simple formulas will be presented. But what I'm going to do now is give a couple of motivating examples. A couple of motivating examples. That will be the practical aspects of this morning. The first block. We're going to start a little analyses, exercises in the second block after the coffee break. But then we're going to talk about, after we presented the motivating examples, we're going to talk about principles for modeling. How should one model these kinds of data to get a feel for it? Without jumping right into doing the modeling, we're going to say why we're doing this kind of modeling. So here's the first data set that we're going to spend some time with. And actually, this data set was part of the two exercises that I announced, and several of you actually asked for and might have been working on. Two exercises, one corresponding to today and the other corresponding to the topics of tomorrow, having to do with LSA data analysis. Today's topic was, exercise was on time-varying covariates, and tomorrow is on selective missing data, non-ignorable missing data. So the data set is the longitudinal study of American youth, and you can get your own CD from them, from the group somewhere in the Midwest. I can give you the details. Started off with two cohorts, and we're going to focus on cohort 2, covering grades 7 up to 12 in U.S. schools, U.S. public schools. And it's each cohort approximately, it is actually multi-level data, students within school. Today we're going to ignore the multi-level aspect. And they focus on math and science. It's NSF-supported activity. We're going to focus on math scores. Now, if you don't like math achievement studies, then you just should free associate into your own application area, be it conduct disorder or consumer behavior or blood pressure development over time. Which reminds me, how many of you go to GOV meetings? Genetics Analysis Workshop meetings? No? Nobody? All right. Well, they have actually interesting setup. They send out data and people do analysis, and then they get together and compare their analysis results. And they provide data from the famous Framingham study. Do you know about that? That classic longitudinal study of blood pressure, coronary heart disease, etc. Very interesting longitudinal modeling aspects. I'll mention a couple of features of that, but it relates very much to what we're teaching here. They have interesting, they have extensive genetic information, SNP information, which you can connect with growth modeling. Anyway, back to mathematics. So it's actually very many multiple choice items that are given. And it's interesting, tomorrow morning we'll talk about how they actually made these scores comparable over time, over all of these grades, despite the fact that the same set of items were not given at each grade. But some, of course, many of the same items were in adjacent grades, but there were many new items sprinkled in across time. An interesting idea, which you probably could benefit from drawing on in many other applications, in psychology, for instance. So here is what it looks like, grades 7 through 12, and the score on the y-axis. And you have here younger cohort males and younger cohort females. Females do a little bit better in the early grades. But then it looks like males overtake females. Males do better in the later grades. If this is a real phenomenon, then you might want to ask, why is that? What is it that makes males do better towards the end? What are the factors for that, behind that shift? And it's interesting, maybe it has to do with these time-varying covariates in the assignment number 1. Well, I slip into saying assignment. It's actually not an assignment, it's an exercise. And please don't hand them in. But this is just the average scores. You know, it doesn't tell you how any one person grows. Actually, nobody might look like this. This is just the average at each time point. And what we really want to do is look at individuals and start our modeling thinking based on individuals. So you have individual curves here. It's on a little bit compressed scale, but you see then 1, 2, 3, 4, 5, 6 individuals and plotting their values of math achievement over the 4 grades, 7 through 10. And you see this person then starts pretty high relative to the others and grow at a healthy rate, and it looks like a fairly linear development. Here's a person who starts slowing down after grade 9. Here's a person who starts very much lower than the others and grows at a very much lower rate. In fact, you can ask, is it the case that those who start higher grow at a higher rate? So you can ask questions about the variation in the starting point and variation in the growth rate over time and covariation between the starting point and the growth rate. So those are 3 things you can ask yourself about in these subsequent analyses. And you can ask, what is it that makes these students differ at grade 7? Their variation, can you explain their variation? If you take the variation as a dependent variable, what are the predictors of that variation? And we're going to be concerned with that quite a lot, trying to predict the variation in the starting point. So this starting point becomes a dependent variable, and it's a latent dependent variable. We're going to call it an initial status dependent variable, or an intercept, which is sort of like a starting point for a growth curve. And you can also ask about the variation in the growth rate. Is this variation explainable by covariates? What makes kids grow differently in math achievement over time? What are the observed covariates that predict that? And then you can ask about group differences, males and females, and try to figure out what males and females have in common when it comes to growth in math achievement and what's different. You can also ask about development on several processes, longitudinal processes, math development and math attitudes. Or in your area of application, it could be aggressive behavior and shy behavior. And you're interested in the relationship between aggressive and shy behavior development, and to see what the consequences of that concoction is down the road. So we're going to talk about that this afternoon in terms of so-called parallel process growth modeling. Parallel process growth modeling and how one approaches that. Here's another data set from the public health area. So here it has to do with the with fetal alcohol syndrome research. And we have a sample of mothers who are giving birth. And it's a sample mixing together mothers who have been drinking during the first trimester and mothers who used alcohol less often. And then mothers we're going to focus on the offspring, the baby. Was measured in terms of head circumference is one of the key measures we're going to focus on. Head circumference at birth and at 8, 18, and 36 months. And we're going to connect that dependent variable with various mothers' variables. So we have here on the y-axis child's head circumference in millimeters, and then the month of observation is the x-axis. And you see the average development is shown by the bold curve here. It's a sharp increase at first and then a leveling off. So it's much less linear development than for a math achievement. So you have to take that into account somehow to capture this nonlinearity. And then here you have also shown the broken lines, which represent the development of children for, I believe, the 8 mothers who drank the most during the first trimester. And it looks like they their babies have a somewhat lower head circumference at birth. You may want to ask if the mother's drinking predictor, the covariate as it were, is a significant predictor of the starting point here of the growth curve, of the variation in the starting point. If you think of the starting point as a dependent variable, can that dependent variable be significantly predicted by linear regression, by mother's drinking? And then it looks like there's more difference in head circumference after 3 years here. Majority of the babies are below the average, and for those mothers who drank more. So you can ask about either the growth rate, is the growth rate lower for mothers who drink more? So again, the dependent variable is growth rate, and the predictor or the covariate or the x variable, we're going to use those terms synonymously, significant for predicting the growth rate. Or you can also, instead of focusing on the initial status here, you can focus on the ending status. We can move our interest to the status at the end here. And that's a topic that we're going to cover within the heading centering. So we can center at the end, so we can predict the growth status here, and to see if we can find significant predictors of that. So, and you can do both. In different analysis, you can predict the starting point or the ending point. Here is loneliness in twins. Maybe you didn't know how lonely twins actually are. You thought, well, they have each other. But no, it's not enough. So here's an interesting data set. This is Dorette Boomsma at the Free University in the Netherlands. All right, so now take a look at this. Apologize for the picture on the right being a little faint, but here's an interesting situation. So they measure people at 4 occasions, 91 up to 2002, so about over a 10-year span. But the age range is 13 to 85. So here's your chance of thinking through this quickly. What does this mean? Okay, so we try to dissect this now. Occasion 1, 1991. Here's the age. It says around 20 here, and you have a variation in ages at the first time point. So this is time point 1, 2, 3, 4, 5. 5, and it says 4 occasions. 1, 2, 3, 4, 5. It should say 5 occasions then. Okay, good typo finding here. So 5 occasions, and these people move forward. They're a little older at occasion 2. They should be 4 years older. It looks like they are. They march on. The histogram moves a little bit to the right, doesn't it? So far we're with them. But then what happens here? Some people get old very much faster than others, it looks like. Well, what they did was, and this is really making the analysis much more complicated. Why did they do that? They sprinkle in people who are a little bit older. I don't know why. I guess they want to cover that part of the age range. So there are new people coming in here. And so we have the old people then marching further to the right in the histogram, and the new people. And I think they sprinkled even more new people. So at the end here, you have a very large age range. So the advantage then is that you can study an age range from 13 to 85, which is pretty impressive. The disadvantage is, of course, that people are born people who are at age 40 were born at different ages. So coming from different locations. So the question is if people are from comparable populations. Are people from a comparable single population, or those who got sprinkled in later, maybe they come from a different population? So this is going to relate to what we're going to talk about in multiple cohort growth modeling. So in here, there are hidden age cohorts, one might surmise. And the cohorts may possibly have different population parameters. Another way of looking at it is, at any given occasion, here's one truth. When you study growth modeling, you have a choice of what the time axis should be. Should it be occasion, or should it be age, or something age-related? So occasion would be 1, 2, 3, 4, 5, right? But at any given occasion, people are of different ages. So if you talk about development over time, it doesn't make much sense to have occasion as the time axis. It should really be age. But then you see at say, the third measurement occasion here, people have very different ages. So your analysis has to take into account that people vary in their ages at a certain occasion. So we're going to talk about a topic called individually varying times of observations. So at say, the third measurement occasion, people vary in their ages, and fourth and fifth as well. So the trick is to take into account individually varying times of observation. So a couple of different issues there, multiple cohorts and individually varying times of observation. And we're going to be able to deal with that quite effectively. Here is what it looks like. It's an item, I feel lonely. It was actually a 3-category item, which got dichotomized because there were essentially only 2 categories used. So it's a binary item. So you have here ages 10 through 60 is what it says here, 10, 15, up to 60. And you have the sample fluctuation, and you have a fitted cubic function. You know, cubic is one more than a quadratic. So not only is it not linear, it's not even quadratic, it's cubic. So here you can study the development of loneliness feelings over the lifespan. So you get increasingly lonely between 15 and 30, and then you get a little happier, less lonely, 30 to 50, and then you tend to get lonely again after 50. That's how it is. The data says. So it's interesting. It's a very nonlinear function. It's cubic. And the other idea represented here is that, you know, we talked about starting the modeling and the descriptives from individual development. We plotted math scores in each grade over time for each person. So we could draw a little picture for each person. Now, what would the picture for each person look like here? I feel lonely, yes or no? You know, it's a bunch of zeros and ones jumping up and down. If you draw a plot of that, you're not going to be very happy looking at it. It's not going to tell you anything. But due to the fact that this is a humongous sample, we're able to group ages together where we have enough people, grouping them in little bins here, so we could plot the proportions and get a feeling for what the growth curve shape is. So at a given age like 35 here, you have a little age range around that where you have enough people that you could plot the proportion who admit to feeling lonely. So there are possibilities to gauge the growth function shape even for dichotomous or binary dependent variables. Another way that we're going to talk about in Michigan is to do latent class analysis. Actually, latent class analysis, which is not an analysis for longitudinal data per se, can be used to capture the shape of a curve for binary outcomes. So you may want to note that. And here's another illustration, another feature that we'll see several times during our discussions here. I feel lonely is very different than nobody loves me. Have you thought about that? So nobody loves me, which growth function would you fit? I would fit the line. Looks pretty much like a line here, a flat line, no slope even. So it's, you have a random intercept, so to speak. You have a random level fluctuating up and down over time, but also over people. But you don't have any trend. So the growth shape is very much different for nobody loves me than I feel lonely. And I mention that because these items were actually first intended to be multiple indicators of the same construct of loneliness. And so the multiple items that were at first summed together. And you know, with only 2 items, you can't really do factor analysis. You have to have at least 3, and you should have many, many more to capture a factor. So you couldn't really tell if they measure the same thing, but if you look at the growth curve shape, you can see that they are different. They're different phenomena. They vary over the lifespan in very different ways. So there's a lesson to be learned about multiple items. We're going to talk about how you deal with multiple indicators. When you have a measurement instrument that have multiple indicators of a construct, how do you do growth modeling of that? But again, that's advanced for tomorrow morning. So change your plane tickets. Okay, now you take a deep breath and try to hold on for dear life, because here comes statistics. All right. So let's think about this. Let's call lowercase n sample size and capital T the number of time points. How would you try to summarize and analyze these kinds of data if you were starting from scratch and didn't get forced into specific modeling thinking? Well, I can think of 3 alternatives here corresponding to these 3 bullets. One is to, I'll use my pointer here actually. Okay. I don't know if Mark is capturing this screen or the other, but here we go. So you could use all of your data points. So think of this as a data matrix. People down as rows and the time points as columns. So n by t data matrix, we might call that. And what do you do? Well, actually, in this case, I back up. In this case, let's say that we have n by t rows, and only one column. The column being the dependent variable. So in this case, math, performance, or head circumference. So there's one variable, one column, and n by t data points. So 100 people have 4 time points, 400 data points. And then you do regression analysis. You have the dependent variable as one column I mentioned, and you have to have something to regress it on. What do you regress it on? Well, time. Say time is x. So you imagine a first column y and a second column x. X is time. And then you do a regression of y on x. And with 100 people and 4 time points, you have 400 observations. And you will then be able to estimate an intercept and the slope. And you could do that analysis for each individual. You know, you have a possibility of regressing each individual's y on each individual's x. And how many time points do you have for the people, for each person? 4 time points. So you should be able to estimate an intercept and a slope for all individuals. But what you don't do then is account for, let's see, in this case, a single regression analysis, I say. Okay, the text confused me here. Back up. So we do one single regression analysis for all people, for all 400 people. I started off correctly, but then I veered off. Okay, you have 100 people, 4 time points, 400 rows, 1 y and 1 x column, and you do a regression analysis, and you get 1 intercept and 1 slope that holds true, that is the same for all individuals. I got confused by my own language here. So you estimate 1 intercept and 1 slope. That's the end result. So what's wrong with that analysis then? Well, 2 things are wrong. You don't account for the fact that individuals may differ in how y and x relate, how the outcome and time relate, nor do you take into account the fact that each person contributes 4 observations. So you don't have independent observations. You have a lack of independence. And that's one assumption then that's violated in the regression analysis. But it's very simple. You summarize it into 1 intercept and 1 slope. Now, the alternative that I slipped into at first is the second one. You can use each individual's 4 data points and do, for each individual, do a regression. So you do n regression analysis. So 100 people, and for each person, you do a regression. And you have 4 observations for each person, y and x, outcome and time. So you get intercept and a slope for each individual. And thereby, you really do account for individual differences. But certainly, you don't account for similarities among the individuals. And now, this is a very good thing to do, though. You could get an idea of development over time for each person. You have the sample development, but you can also fit, say, a line for each person. So you could do 100 regression analysis, even though you only have 4 time points for the people, to get a feeling for what the lines look like. Do they point upwards or downwards? Now, so these 2 are extremes. Here's one analysis, a single analysis, and here is 100 analyses. What you really want is the best of both of those 2 ideas, and that's what the third bullet is about. You use all of the data points, but you do a single analysis. So it's not like bullet 2, where you do 100 analysis, but it's like bullet 1, where you do 1 analysis. But you don't do a regular regression analysis. You do a random effect regression analysis. A random effect regression analysis. So that's going to end up giving an intercept and a slope for each individual, which is just like what you get in bullet 2. So when you can underline for each individual and point up like that, say just like for bullet 2. But at the same time, it accounts for similarities among individuals by saying that they all come from a single population, which is how we acted in bullet 1. So a single common population may draw a little line up to bullet 1, capturing the idea of bullet 1. And at the same time, then, we're going to model the non-independence of observations and so we are not hurt by a violation of independence. So I would say that you don't want to do this. There's no need to do this. It's just straw man set up to be knocked down. This you might want to do just to learn more about the data features, but this is really the analysis that we're going to focus on for the remainder of this course. It gets the best of both worlds, of the previous 2 bullets. And here's what it looks like. So we're going to look at y as a dependent variable, and we're going to look at the subscripts a little bit here. it's time point t rather, for individual I. So time point and individual, you have it written out here. And this equation 1 should just be thought of as standard linear regression. We regress y on x. So we have the dependent variable and the independent variable x, or covariate x. X is a time-related variable. It could be age, for instance, or grade. And then we have a residual, which we're going to call epsilon out here. Epsilon is just a residual. So we're going to focus on the two terms here. The term sitting by itself here is an intercept, and the term multiplying x is a slope, just like in regression. So intercept and slope. And it's just that we've given it a funny notation here. It's the Greek letter eta, E-T-A, eta, eta 0 and eta 1. Eta 0 intercept, eta 1 slope. And that is like regular regression, right? Except we usually say alpha and beta, or A and B here. But we want to emphasize connection with latent variable modeling, where eta is used for factors. And it's a factor in this sense that we have these eta 0s and eta 1s are random effects. And random effects simply means it's a quantity that varies across people. So the subscript I here for eta 0 and eta 1 signifies that it is a variable that varies across individuals. That's what's meant by random effect. So it's not like your old linear regression textbooks where you have only one intercept and one slope. That's true for everybody. That's the population values. Here, you have random intercept and random slopes. They vary across people. So capturing the individual differences of bullet 1 here, but we're saying that those random intercept and slopes are coming from one and the same population. And that's described by equations 2. In equation 2, etas are dependent variables because they're on the left-hand side of the equality. So here's the intercept eta 0 equation, and here's the slope eta 1 equation. And they are, in turn, linearly regressed onto an observed variable w. So this is just like a linear regression. You have a dependent variable, you have a new intercept, you have a new slope. We call that intercept alpha, and a new slope gamma, and an observed variable, predictor, covariate, x variable, except we call it w here. And then a z or a z, the Greek z, which is a residual, just like epsilon was for equation 1. And then the same thing for the slope here. So this is then with random effects as dependent variables, but it's still a linear regression. And here it's a traditional linear regression in part. It's a traditional linear regression because there are no subscripts here now. There's no subscript I should say, for alpha and gamma. They don't vary across people anymore. It's the equation 1 that varies across people. So let's take an example. Let's say that y is math achievement, and x is grade, and we have 3 students, student 1, 2, and 3. Student 1 tends to start higher than the other 2 and grow a little bit faster. So student 1 has a higher eta 0 I value. So student 1 has the starting point value eta 0, 1. That's where the person starts, and then the person grows with the rate eta 1, 1. And then for individual 2 and individual 3, they start lower, grow slower, so lower eta 0 and eta 1 values. So these, if you like pictures, this is a picture of individual differences in development over time, right? That goes well together with individual difference studies of psychology. And it also ties very nicely into statistics because statisticians like to build their models from the person level up. So you have then a model for the person, I. So these subscripts really are meaningful. You know, the statisticians' love of subscripts, I, correspond directly to the psychologist's love of allowing for individual differences in development. It's one and the same thing. That's equation 1. Now, for equation 2, where the random effects become dependent variables, we don't have variation in the coefficients anymore. It's standard regression. So eta 0 is linearly related to W. You have a negative slope here, which implies that gamma 0 is less than 0. So you may want to write here, gamma 0 less than 0. Negative slope. So for instance, if W is poverty background for the student, the higher the poverty, the lower the starting point in math achievement in grade 7, for instance. So poverty increasing makes for a lower and lower starting point. And likewise for equation 2, as poverty increases, perhaps the growth rate decreases. So the student doesn't gain in mathematics performance as quickly due to lack of resources or whatever. But those are regular linear regressions. They just look funny. They're regular in the sense that we don't have any subscript, but they're not regular in another sense, namely the dependent variable is latent. It's unobserved, right? We don't observe these these intercepts and slopes. We don't observe them. They are latent variables, and it's of the specific latent variable kind called random effects. And in passing, I should just say a random effect is a fixed effect when its variance is 0. A random effect is a fixed effect when its variance is 0. Because then, you know, there is no variation. It is just like a regular coefficient, regression coefficient, which would say that everybody starts at the same spot or everybody grows at the same rate. But in any case, there you have the idea, and it's expanded then in terms of slide 26. So you can conceptualize this. We have this, you know, custom made for you. You're one of either 3 categories of people. You're a visual person who likes to see how things grow, or you are a formula person. You just love equations 1, 2a, and 2b. Why would you bother with anything else? That tells the whole story. And believe me, I meet all of these people. And then there's the third kind of person who prefers the model diagram instead. So these are 3 equivalent ways of saying the same thing. So let's just go from 1 to 2 to 3 together. So again, individual differences in development over time. We talked about that. These are 3 different individuals. X represent a time axis, so you have time point 1, 2, 3, 4, 5, etc. And the formulas are simple. Equation 1 is describing the math achievement outcome and how it varies across time here and across people, of course. And then equations 2a and 2b, the dependent variables are the random effects, and describing variation across person here. It's no longer across time, but across person. And then we can introduce a term already here. If you're familiar with multi-level modeling, this is their level 1 equation, level 1, and these are their level 2 equations. So level 1 has to do with variation across time. Level 2 has to do with variation across people. And you can check that that's true because level 2 only has I subscript. That's the only thing that varies. So subscripts tell you what varies. So level 1 and level 2, now we can draw this in latent variable terms and say for the example of 4 time points, so you might want to write cap t equals 4 here. We have math achievements in grades 7, 8, 9, 10, Y1 through Y4. We draw 4 boxes for observed variables. They're dependent variables. And we're saying, we're interpreting equation 1. We're saying that these random effects, eta0 and eta1, are latent variables. And so therefore, they're circles. So latent variable is something that's not observed and something that varies. And etas fulfill both of those in this case. So those random effects influence the y's. So the initial starting point and the growth rate, initial starting point and the growth rate, will influence where you are on y at the 4 different time points, right? So that's what this picture says. And you recognize then that that is exactly what equation 1 talks about. And you then recognize, if you were here in March, that this is the measurement model of a factor analysis model. This is we're going to call this a CFA model, confirmatory factor analysis model, which will be clear in a second why we call it that. Level 2 has etas as dependent variables, so etas have arrows pointing to them, influenced by the covariate W. So we have gamma 0, the gamma 0 here sitting on this path. You might want to write gamma 0 here. And gamma 1 on that path. Standard linear regressions, except for the fact that the etas, the dependent variables, are latent. So that's level 2, which then in latent variable structural equation modeling terms will be called the structural part of the model. Structural part of the model down here, measurement part of the model up here. And the interesting question then is, well, and then you have the residuals, epsilon sitting up here, 1 for each time point, short arrows, and the z's, z0 and z1, sitting down here, and they can be correlated, those z's. Epsilons can also be correlated across time, and we'll see examples of that. Now, you ask, where did x go? And I'm glad you asked that. Where did x go? It's a very good question. It's funny how we'll see x appear or go in 2 different directions depending on which modeling framework you come from. In this case, etas are the variables, and x is a coefficient. If you think about it, we actually now turn things around. We started saying that etas were coefficients, and x was the variable, right? X was time variable. But now, we're going to present one framework, namely the SEM. I'm going to say SEM for structural equation modeling from now on. The SEM, or CFA framework, to growth modeling. Instead of saying that these are coefficients, etas are coefficients and x is a variable, we're going to say now that the etas are a variable and x is a coefficient. So the x's are going to be up here. The x's are going to sit up here. So first of all, if you look at eta, how does eta influence the y's? Well, irrespective of t, eta is the same. Eta influences y the same for all t's. There's no t here. So we can imagine that there is an invisible 1 multiplying eta 0 here. So the paths from eta 0 to the y's are 1, 1, 1, 1. Because it's the invisible unit multiplier for all time points for eta 0. But for eta 1, the multipliers are x. x1, x2, x3, x4, sitting over here. So the x's end up here in this first framework for doing growth modeling, which we're going to expand on in a second. So if you're familiar with CFA and SEM, these coefficients are all fixed, and they turn out to be fixed factor loadings. Fixed factor loadings being the regression coefficients of y on factors, in this case y on random effects. So they're all fixed, 1, 1, 1, and x1, x2, x3, x4. And the question is, then how can this model ever fit with such a restrictive model with fixed loadings? And the answer is, it's just the right kind of modeling framework that will actually do quite well in many cases. Just the right kind of type of model. So if you look at this, this is an SEM, structural equation model. And then, of course, the reason that we put it into this latent variable framework is that you get all kinds of interesting associations here. For instance, if you have a W that's hard to measure well, maybe you want to try to measure it by a measurement instrument that has multiple indicators to take into account measurement error. If you have measurement error in a covariate W here and ignore it, you will attenuate the influence. You will underestimate the influence typically on the growth factors. So you can have a latent covariate here with multiple indicators. Or, staying with the observed, you can have effects from W to Y directly. There may be some time points where the W is especially influential. You note that W influences Y's indirectly through the random effects, through the growth factors, as we will call them, indirectly this way. So the ADAs are actually mediators, which resonates with psychologists, but you can have then direct effects on top of the mediation effect. So that's an extension that is easy to make in this framework, and you easily will think of it when you're in this framework. And the dependent variable side, you can have, instead of observed variables, it could be a factor at each time point, where the factor at each time point is measured by multiple indicators. So a measurement instrument for the dependent variable side here. And of course, you can put this model into a much bigger framework where you have add other parts to it. We're going to talk about that in terms of so-called embedded models. So now, the way into this topic that I chose was then one of several possible frameworks. On slide 28, you have some of the more important frameworks. The framework I talked about was the SEM framework. And the kinds of growth models that you can do are all within this SEM circle. But we're gonna expand on that framework in several different ways and talk about the multi-level framework, often connected in the US with the HLM, hierarchical linear modeling approach, and also the HLM program. And that's covered by these kinds of, this circle, which partly overlaps with SEM, but partly adds some other features that you cannot do in SEM, while SEM has its own unique features that you can't do in the HLM framework. And then you have the so-called mixed linear, statistician's term for what we're doing here, mixed linear model, where mixed stands for a combination of random and fixed effects. Mixed implies random and fixed effects. Has nothing to do with mixture that we're going to talk about later on. SAS-proc mix is a good example of that. Almost the same, covers almost the same kinds of things as in HLM. And then what I would like to state then is that we have a distinctly different framework from all of those, which I just call the latent variable modeling framework, which is used in Mplus, which is covered by this square, which incorporates all of what SEM does and much of what's done in the other two frameworks. Has a lot of unique features out here, unique, but misses a couple of features of these two other frameworks, like cross-random effect is one example for multi-level modeling. Not so much missing in the pure growth modeling area. And then with the arrows pointing upwards saying that we'll keep developing this framework, so the box is going to get bigger and bigger and expand upwards. But let me tell you a few things about the differences between these frameworks. Now, I don't know which slide to have open here, but probably this one. So in words, three frameworks, multi-level, mixed linear, and SEM growth models. So comparing three of the four frameworks. So multi-level mixed linear models, I would say they're about the same. They just is different ways of formulating the same thing. SEM differs from multi-level mixed linear models in two ways, which we will encounter here. Treatment of time scores. Time scores are the x's. If you look at slide 26, x's down here, I call them time scores. In multi-level and mixed linear models, they are data. Data that you read in, just like y, you read in x. And that's how we started talking about these kinds of analyses. And individuals can therefore have different times of measurement. So that we covered the loneliness of twins example, because at a certain occasion, people are of different ages. So this is the individually varying times of observations. But in the SEM framework, time scores are not varying across people. They are parameters. In this case over here, they were fixed parameters, fixed to 1 for eta 0 and, well, sorry, fixed for eta 1 rather, at values x1, x2, x3. They do not vary, and you see then the subtlety here in equation 1. There's no subscript I. There's only a subscript T, no subscript I. So the SEM framework is limited to having the same age for people at a certain time point. Another example that SEM can't handle is you have a treatment, you ask people to come back after 1 month, and some people come back after 4 weeks, some come back after 6 weeks. That time difference can be important. So the second time point, second occasion, varies in distance from the treatment. So that would call for x sub t I, and the SEM framework would not be enough. So in the SEM, time scores are parameters. You can't have individually varying times of observations, but on the other hand, you can therefore, since they are parameters, you can estimate them. And we're going to see examples of that being a very useful way to find a flexible growth curve. And then the treatment of time-varying covariates. Time-varying covariates is something, is a covariate that has subscript T and I. It varies not only across people, but it varies across time, like math course taking over the different grades, which is an example we're going to deal with. And in the multi-level mixed linear models, those can have random effect coefficients. So a slope that can vary across people. Coefficients vary across individuals. Whereas in the SEM framework, they are fixed coefficients. They do not vary across people. On the other hand, they can vary across time. So we're going to go through that example of exercise number 1 and look at those differences. So there are subtle differences here. In terms of time-varying covariates, this equation 1 doesn't even include them yet. I wanted to keep it simple. But that is essentially a key difference for those frameworks. Here is the random effects multi-level and mixed linear modeling comparison. If you start with the multi-level model, I recommend that you read the Rowden, Bush, and Breich book. We have all the references in the back. And level 1 in our notation is as before, random intercept, random slope, time-related variable, but now you have x sub ti. And WTI is now a time-varying covariate. Time-varying covariate. So it varies across time and person. And kappa, this K-looking thing, kappa, has a subscript I, so it's a random effect. So saying that for the same amount of math course taking in grade 8, individual 1 benefits more than individual 2. This kappa sub I. So that sounds like a very useful thing to have. And level 2, we already talked about level 2 there. Mixed linear model is just writing out, splitting up the fixed and random parts. I think the mixed linear model formulation is a little bit more statistical and less pedagogical. But essentially, if you go back here on slide 30, mixed linear model comes about just by inserting these random effects of level 2, putting them into level 1, and writing out the whole resulting equation. You get it like this. And in SAS-proc mixed, then you will see something like in the output time times W, which looks really mysterious, perhaps not intuitive. But time times W sits here, where you insert the slope into equation 1, and time is x, W is here. Time times W refers to gamma 1. Who would have known? So gamma 1, if you look over here, it's very pedagogically oriented in slide 26. Gamma 1 is the influence of the covariate onto the growth rate. So I think multi-level modeling formulation wins in terms of pedagogy. But anyway, lots of people have contributed to the mixed linear model framework, and lots of programs corresponding to it. As opposed to that, then, is the SEM framework, which we had here. X sub t, no subscript I, and kappa sub t, no subscript I. So I won't belabor that point anymore. Let me just show you probably the only time here, almost the only time, we show matrices. Mixed linear model can be written like this as well in terms of formula. So if you see this, x times alpha, z times b, know that that is a mixed linear model and that it is the same thing essentially as a multi-level model formulation. This we don't have to talk about. Here's an important slide, though. Here's an important slide. We're going to talk about growth modeling the way we started on the left screen, 26, is what we have at the top, the first bullet on this slide, 36. But there's an alternative way of dealing with it, which is represented by the second bullet. But let's start with the first bullet and just repeat. The way we draw in the picture on slide 26, your left screen, is recaptured here, top right, where the intercept is now called I, that's the old eta 0, and the slope is called S, the old eta 1. And the equation is therefore Y on I and S times time plus the residual, and then we regress I on W and S on W. We're going to call that the wide approach, wide multivariate approach. Multivariate because we have, with 4 time points, one outcome, like math achievement of 4 time points, gives us a 4-variate vector as the observation vector for each person. So multivariate because we have 4 things rather than 1, the 4 things arising from 4 time points. So it's 4 time points, and the contrast to that then, so think about the data here. The data is people by the columns of Y and W. Now instead, you could treat the data in the long form, where instead of having 4 Ys here, you would have 1 Y on 4 lines. So you have the repeated measures nested within individuals. So it's a univariate 2-level approach. And that's perhaps the more common one in the HLM and SAS-Proc mixed approaches. It's a 2-level approach. So you have on level 1, or in Mplus we call level 1 very often, the within level, and you have a level 2, the between level. So on the within level, you have the regression of the dependent variable math score Y on the time variable like x sub ti. And we're going to define a random intercept and a random slope. This is really the topic of the multi-level 2 days in March 2009. Random intercept and a random slope, like eta 0, eta 1, which on the level 2 become dependent variables, eta 0, eta 1, latent dependent variables regressed on W. That's level 2, or the between level. So what I'm saying is you could do growth modeling by either approach. And if you specify this model in a certain way, you will get exactly the same results as if you did it in a 2-level approach. But I will argue that this multivariate approach is more flexible. It's more flexible. You can do more flexible modeling, more realistic modeling with that approach than you can with a 2-level approach. So most of what we're going to do is talking about the single-level multivariate approach. It has a disadvantage, though, that is not shared by the second approach, the 2-level approach, Namely, the multivariate single-level approach suffers when you have many time points. So if you have 100 time points, for instance, you will get a vector of length 100. And that's heavy computation even with today's computers. In the two-level approach, instead, even with 100 time points, you have only one dependent variable. It's univariate, right? The 100 time points becomes 100 members of the cluster of individual I, and the computations don't suffer from that at all. So just so you know that there are these two approaches, and if you specify the multi-level approach in a certain restrictive way, you get exactly the same estimates as in the univariate two-level approach with data range as long. But we're going to stay with the first approach. So 37. Now, let's skip that slide and go to this slide. Before we move too far in to the growth modeling approach, we should note that there are many different models that you can consider for longitudinal data. And certainly we're going to talk about survival analysis tomorrow, but even so, you have you must not forget the autoregressive model, which is then contrasted here with the growth curve model. So we talked about the growth curve model, and it says that the math achievement development is a function of the growth factors, which represent how much you knew about math when you came in and how much you learned as you went along, I and S. As opposed to that, then the autoregressive model says that your math achievement score at time 2 is directly influenced by the math achievement score at time 1, and onwards and upwards here. So you have direct influence from the observed score. So Y2 is influenced by Y1, whereas in the growth model, Y2 is influenced by I and S. So very often in the past, people dealt with autoregressive models, and then growth curve models became more important. But I think your application should really tell you which one is the best one to go with. So you should ask yourself, for math achievement, for instance, the performance in grade 8, is that a direct function of the performance in grade 7? How would that be? So the score that you got in grade 7 influences the score that you got in grade 8. That's almost like test performance in grade 7. If it was good, then it influenced test performance in grade 8. Maybe in that case, it's more realistic to say that grade 8, Y2 here, is a function of how much you really knew at grade 7 plus how much you've learned since then. A learning process represented by I and S influencing Y2. Whereas in other applications, it may be the actual observed value that influences Y2, observed value of Y1 in this case. And then you can think of combinations where most of the influence is from I and S, but perhaps is direct influence between the Y's on top of that. And that would then be the hybrid models that have been studied by Curran and Boland, McArdle and Hamagami, and are represented in the Boland and Curran longitudinal modeling book. You have the references in the back. So there are these other possibilities, certainly. When you come to Michigan, talk about mixture modeling, latent class modeling, you're going to see an example of an autoregressive model in the form of so-called latent transition analysis. Whereas here, in these 2 days, we're not going to talk about autoregressive models at all. We're going to just put them by the wayside. It doesn't mean that they're unimportant, but they are not part of what we're talking about here. Now, why do I emphasize the latent variable framework? We talked about 4 frameworks. So far, I really only talked about 3. The SEM framework, the HLM multi-level framework, and the mixed linear model, the SAS-proc mixed type of framework. Here, the 4th framework is the latent variable framework, the box that keeps moving upwards. Why am I focusing on that? Well, I think it's a really good vehicle for unifying several different topics like we talked about, but also a good vehicle for looking at growth modeling in a very general fashion. So in that framework, which is the one that Mplus has adopted, you can handle time in terms of parameters, the first SEM approach we talked about, x sub t, parameters that can be estimated time scores, as we will call it. That's represented by the first bullet, flexible curve shape. But if you do have data where you have individually varying times of observations, like for those lonely twins, you can enter the time scores x sub ti as data and have that flexibility. So you have a choice. Moreover, in this latent variable framework, you can easily do what's a hallmark of SEM, namely do regressions among random effects. You can let the growth rate be influenced by the starting point, for instance, and we'll show you some interesting moderation interaction examples of that today. And in the latent variable framework, you can deal with multiple processes, math achievement, math attitudes, for instance, very easily. And as we will see tomorrow morning, you can easily model zeros, variables with strong floor effects, which turns out to draw on a lot of latent variable thinking. And you can easily deal with multiple populations, namely multiple group analysis in the SEM fashion, males and females or multiple cohorts. Multiple indicators of a latent dependent variable construct, growth for the latent variable construct, measured by multiple indicators. And a growth model that's only a part of the full model that you're interested in. You can combine a growth model with a latent class model, for instance, or we'll see examples of that. And then finally, the generality of the latent variable framework, bringing in categorical latent variables. So far we talked about random effects, the continuous latent variables, but for more fundamental differences in development, qualitatively different developments, you have to bring in categorical latent variables, so mixtures, latent classes. And that's a growth mixture topic, which then is not part of these 2 days, but will be part of the second day in Michigan. So that's the fourth framework, which combines the previous frameworks.